This video is a lesson on intermolecular forces. Before intermolecular forces, we should revise a bit on dot and cross, the SEPR, and also whether it has dipole moments or not first. Then we will determine the intermolecular forces. Let's take these two examples, PF3 and BF3. Let's draw the dot and cross first. T has 5 outermost electrons and B has 3 outermost electrons, and they're all going to be bonded to 3 fluorine atoms. So F, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. I insist we always draw all the electrons, all the outermost electrons, so that we don't forget during exams. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4, 5, 6, 7. So next we need to determine the number of lone pairs and bond pairs. So there's 1 lone pair, 3 bonded pairs. So the shape would be trigonal pyramidal. It looks something like ammonia. And BF3 is trigonal planar, as it has 3 bonded pairs with no lone pairs. So I'm going to draw the shapes here. P lone pair, PF3. And B, since there's no lone pair, it's flat, it's planar. Okay, both PF and BF are polar bonds, but as a molecule, do they have a dipole moment? So P compared to F is more electronegative, so it will pull the electrons towards itself, the shared pair of electrons. And for B and F, also F is more electronegative, so it will pull the shared pair of electrons towards itself. So pull, pull, and pull, 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 and pull. Let's see if it goes back to 0. So if it pulls down and down and down, nothing's pulling it back up, so it doesn't go back to 0. So this has a dipole moment. As for BF3, let's start with this one, so down. Let's start with 0, so down, and go this way, so this way, and this way. So go this way. It goes back to 0, so there is no dipole moment. So knowing this, which one has a dipole moment and which one doesn't have dipole moments, we can determine the intermolecular forces. We will cover 3 intermolecular forces. The first one would be London force, which is the weakest one. London forces is also known as instantaneous dipoles. It's also known as induced dipoles or temporary dipole. Slightly stronger intermolecular force would be permanent dipole. Or we can also call it dipole-dipole forces. So dipoles and another side of dipole forces. Okay, these, we can also call them, both of them together, as van der Waals forces. The next one would be the strongest intermolecular force. That would be hydrogen bond. Okay, if something has no dipole moment like BF3, so it will bond with each other by London forces. So that forces is instantaneous, or it's just induced or temporary. So there's no permanent one side of it that is more negative than the other. The whole molecule is evenly distributed. So if the electrons go around and maybe at one time it's closer to this side, so this will be negative and the other end will be positive. So that is why it's not permanent, it's temporary and it's instantaneous and it's induced. So if there's another molecule beside it, since here is positive, it will attract the electrons towards this side and the other side will be positive. So this force here, a delta negative and delta positive here, that is a London force. Okay, but for something that has one side that is more negative than the other, so in this case, we said just now PFF is more electronegative. So obviously this side of the molecule is more negative and this side is more positive, and this is permanent. It's always like this, it doesn't move. Whereas for this one, at another point, maybe the electrons move towards this side and this will become negative and this will become positive. The negative here will induce this side to become positive and therefore the other side negative. So it's not permanent, it's where the electrons moved. Whereas for permanent dipole, it's permanent. We know that this side is more positive and this side is more negative. So that is why we need to know how to draw the dot and cross, know the shapes, and determine whether it has a permanent dipole, has a dipole moment or not. Then we will know whether it bonds using a London force or permanent dipole. So besides that BF3 we saw just now, a very straightforward example of things that bond with each other via London forces would be our halogens. So for example, Cl2. So obviously there's no one side that is more negative or positive, it's evenly distributed. So if these electrons happen to be on the left side, so this side will be negative and this side will be more positive. So if I have another Cl beside it, Cl2 here, so it will be induced, the electrons will be attracted to this side and therefore this side become positive. So this is London forces. London forces, the strength of London forces is affected by the number of electrons and also whether there's branches or not. Okay, this one I will use an organic compound to show that. Okay, for a number of electrons, an example would be Cl2. If you compare that with Br2. So one Cl2 to another Cl2, they bond by London forces, and Br2 to another Br2. That's also London forces, but it's stronger because there's more electrons in Br2 compared to Cl2. So the strength of London forces is stronger. This is why Cl2 is in gas and Br2 is in liquid, because it would have a higher boiling point, or it's less volatile because its London forces is stronger. It has more electrons in one molecule. Okay, what if I have isomers of C4H10? So C4H10 can be more than one organic compound, but if they're isomers, they would have the same number of electrons. So let's see how I draw it with branches and without branches. So C4H10, it could be a butane, or it can be a methyl propane. So there's branching here. straight chains have stronger London forces compared to branch chains. So let's imagine them like this. Straight, 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 and all stacked up together. They can go closer to each other. So the London forces are stronger here compared to if I have something that is in this shape. So there's gap between them because of the branching. So they're further apart from each other. Their London forces are weaker. So this is stronger and weaker. So branches will cause the London forces to be weaker compared to if the chains were straight. Next, dipole-dipole forces. So these are not induced, it's permanent. So for example, if I have a HCl, so obviously in a HCl, Cl is much more electronegative. So that will be the negative side of the molecule and H will be the positive side of the molecule. So if this bonds with another HCl, the H would definitely face the Cl. So that positive can bond with negative here. And it's delta negative with delta positive. So these are dipoles. So I draw another HBr here. So same thing, it's dipole-dipole forces here. So delta negative here bonds with the delta positive. So in the same way as HCl. But which one is stronger here? So in this case, we will compare their difference in electronegativity. So H, the difference with Cl is larger compared to H and Br. So let's say that comparison. So H is 2.2. Of course, it's more different with a Cl. Cl is 3.2, while Br is only 3.0. So there's a larger difference here, which means the permanent dipole in HCl is stronger than HBr. But remember this, something that has dipole-dipole forces, it will also have London forces because it also contains electrons. Now, sometimes the electrons is a lot, so the London forces can overcome that permanent dipoles. So it might be even stronger than the permanent dipoles. So we can compare the boiling points of HCl and HBr to find out which is higher. So if the HCl boiling point is higher, that would mean that the permanent dipoles are stronger. But if HBr boiling point is stronger, that would mean that its London forces is stronger because it has more electrons here. Okay, this graph of melting and boiling point is just for illustration, so it's not the actual values. So I'm just showing a comparison here. So CH4, SiH4, GeH4, and SnH4, they're all from group 4. So from group 4, but going down the group, there's more and more electrons. Although they look the same, it's tetrahedral. But since there's more and more electrons, their London forces will increase in strength down the group. Therefore, the melting and boiling point will increase as well. Okay, we'll compare that with the other groups later. Okay, the next intermolecular force that we want to cover would be hydrogen bonding. Hydrogen bonding has two criteria. The first criteria is that, of course, it must have a hydrogen. And this hydrogen, the criteria for this hydrogen is that it must be covalently bonded to an NO or F. So this must be there so that it's very delta plus, while the NO or F is delta negative. So NO and F are the most electronegative atoms in the periodic table. This is why hydrogen bonds can be formed. Okay, the second criteria is that we must have a lone pair of electrons. And this lone pair must also come from NO or F. So I'll just jumble it up a little bit. So this is a hydrogen bond. hydrogen bonding. Okay, if you look at this hydrogen bond, you'll find that it looks a lot like the permanent dipole. And in fact, it is a permanent dipole. It's just an extra strong permanent dipole. It's just that the delta negative and the delta positive has a very different electronegativity. So if you have a H here, it's 2.2, and then NOF is 3, 3.4, and 4. So it has a large difference in electronegativity. This is how hydrogen bonds are formed. Okay, whereas permanent dipole is a similar thing, but it's not with NO or F. So if we had like Br just now, that would be a permanent dipole and not hydrogen bond. So hydrogen bond is especially for things related with NO or F. There must be a hydrogen that is covalently bonded with NO or F and lone pair that is from NO or F. So this is the first criteria that I drew just now. Hydrogen, delta plus, that must be covalently bonded to an NO or F. This makes the delta plus and delta minus really different. So there's a huge difference in the electronegativity. Okay, second criteria is the lone pairs. Now for this criteria, the NO or F need not be covalently bonded with any H. It can be something else, can be a carbon or something else, as long as it provides the lone pair. So delta negative here with the delta positive here, when they bond with each other, that is our hydrogen bond, and these are the two criteria. So the atom here can be anything else. So knowing that NO or F gives us hydrogen bonding, so we're going to look at water, ammonia, and hydrogen fluoride. So they all contain hydrogen bonding. So I'm going to draw two water molecules here and see how many hydrogen bonds can be formed. So one here and one here. So if I'm just counting how many hydrogen bonds can we form, I'll just draw one here. It doesn't actually bond like this, but I'm just trying to count. So there's 1, 2, 3, 4 hydrogen bonds for 2 water molecules. So I can say there's 2 hydrogen bonds per molecule. Let's do the same for ammonia and HF. So there's a hydrogen bond here. So the H that's from NOF and the lone pair that is from the N. And let's say there's one more here. Of course, it don't actually bond like that, but just for counting purposes. So there's 2 molecules here. So there's only 2 H bonds per 2 molecules. Therefore, I only have 1 hydrogen bond per molecule. Why so? Because although there's abundance of hydrogen still, but the lone pair is limited here. So I don't have any more lone pairs to form hydrogen bonding here. Let's calculate for HF. So here, form a hydrogen bond. And let's say here, form another hydrogen bond. There's plenty of lone pairs still, but hydrogen is limited here. So I ran out of hydrogen. There's only 2 hydrogen bonds for 2 molecules. So I only have 1 H bond per molecule. that would be the same as ammonia. So whose hydrogen bond would be stronger? So when we compare these three, obviously water would have the strongest hydrogen bond because there's 2 per molecule. And for HF and ammonia, there's only 1 per molecule each. So the next thing to compare would be their electronegativity. So N is 3.0 while F is 4.0. 4.0 is more different with this 2.2. So the hydrogen bond is stronger in HF compared to ammonia. So strongest, second, third. So I'll put water, HF, and ammonia here with respect to how strong were the hydrogen bonds just now. So number 1 is water, so I put it at the top. Second is HF because it has a more different electronegativity. So I put it second place here. And then ammonia and CH4 doesn't have hydrogen bonding, so it's much lower. Okay, what about the others in the same group? Okay, in the same group as nitrogen, so we have NH3. So I'll draw PH3, ASH3, and SPH3. So you'll find that the boiling points increase going down the group, except for ammonia, it's an anomaly because of the hydrogen bond. So there's an existence of hydrogen bond in NH3, which is why it's much higher compared to its own group. So PH3, ASH3, and SBH3, the increase here is affected by van der Waals, which is London force and permanent dipoles, whereas NH3 is affected by hydrogen bonding. Same goes for the next group. So we have HF, HCl, HBr, and HI. So it goes down, up, up, up. So same thing, HCl, HBr, and HI is affected by the van der Waals, which is permanent dipoles and London forces, whereas HF is affected by hydrogen bonding. Same goes for water, so H2O, H2S, H2SE, H2TE. So again, down, up. So up is because of, so this portion is all because of van der Waals. Van der Waals includes London forces and also permanent dipoles. And these NH3, HF, and water is affected by hydrogen bonding, which is much stronger. That's why they have higher melting and boiling points. Let's look at some examples here. So A, this part of the carboxylic acid, this is the R part of the carboxylic acid, the electrons are evenly distributed. And CCl4 looks like this. So it will cancel out all the dipoles. Therefore, there's no dipole moment here. So if there's no dipole moment, therefore this is induced. So A is London forces. Okay, B. There's lone pair of electron that came from NO or F, and then there's a H that is covalently bonded with NO or F. So B is definitely a hydrogen bond. C, okay, there's a lone pair here that it's from NO or F. It's bonded to a H here that's delta plus, but this H is not covalently bonded with NO or F, it's a Cl here. So C is only a dipole-dipole. It's not a hydrogen bond because it doesn't fit the second criteria, where it says that the criteria has to be that the H must be covalently bonded to NO or F. Okay, and D, this one. There's a H that's covalently bonded with NO or F, it's O here, and it's bonded to the lone pair that is from this N here, that's from ammonia. So the last one is a hydrogen bond. So this is how we determine what intermolecular forces are holding them together.